Welcome. Today, we're discussing atmospheric mercury pollution, a significant global environmental and health challenge. Mercury, a potent neurotoxin, travels vast distances in the atmosphere before settling into ecosystems, posing risks to both wildlife and humans. Let's look at the chemistry. Atmospheric mercury primarily exists as gaseous elemental mercury, or GEM. It's long-lived, allowing for global transport. The key transformation is its oxidation into gaseous oxidized mercury, GOM, or particulate-bound mercury, PBM. This process involves oxidants like ozone, hydroxyl radicals, and, critically, halogens such as bromine and chlorine, especially in marine and Arctic regions. Sunlight, temperature, and aerosols also influence these reactions. Once oxidized or bound to particles, mercury is removed from the atmosphere mainly through wet deposition, rain and snow, and dry deposition, where it settles onto surfaces. Interestingly, some deposited mercury can be reduced back to its gaseous form and re-enter the atmosphere. The global impact is substantial. Mercury pollution crosses borders, necessitating international cooperation, as seen with the Minamata Convention. When mercury deposits in aquatic systems, it converts to highly toxic methylmercury, which bioaccumulates in food webs, leading to high concentrations in fish. This primarily affects human health through fish consumption, causing neurological and developmental problems, especially in the young. The Arctic is a hotspot for mercury deposition due to global air patterns and vulnerable food webs. Reducing emissions from sources like coal burning and gold mining is vital. While this decreases atmospheric levels and deposition, ecosystem recovery can be slow due to existing mercury. Effective monitoring is essential to track mercury's sources, transport, and the success of reduction policies. Global networks like GMOS and AMNet provide crucial long-term data. Instruments measure the three main forms, GM, GOM, and PBM. GM is often measured using atomic fluorescence spectroscopy. GOM and PBM are more challenging but are typically collected on denuders or filters before analysis. Passive air samplers are increasingly used for wider spatial coverage, especially in remote areas. Emerging techniques like mercury isotopic analysis help trace sources and understand transformation pathways. Satellite data also provides context by monitoring factors like aerosols and bromine monoxide, which influence mercury cycling. This comprehensive monitoring helps refine models and guides efforts to combat this global pollutant. Understanding and reducing mercury pollution is crucial for protecting human and environmental health worldwide.